Technion in Haifa, right? Yes. We will speak today about infinite range mutually catalytic branching model. Please welcome.
Thank you. Okay, thanks for giving me the opportunity to give a talk here on our recent work on the infinite range mutually catalytic branching model. This is joint work with Achim Klemke from the University of Mainz, and so we worked quite a while on this on this model, and it ended up in 3 papers. One of them was accepted already to the annals of probability, and we are quite fascinated by the construction of the model, since we didn't know when we started, we didn't know the answer in advance, and I'll happy to share with you what we have done. So the model is somehow extension of the so-called mutually finite rate mutually catalytic branching model, which was introduced by Dawson and Perkins on the infinite colony space. They talked about the following system of SDEs. So you have the lattice ZD, and on each side of the lattice you have 2 types. So population consists of 2 types, and so on each side you have 2 types, y1 and y2, and they solve the following pair of equation, and you go around all these sites on ZD. So where A is the matrix, which is the generator of Markov chain on ZD, and assume for simplicity that it's symmetric. This was one of the assumptions of Dawson and Perkins. And one can think about this equation so that you have particles which are moving around with generator A, and you have a noise term where which is in some sense is what is left from the branching from the pre-limiting picture. I'll talk in a second about the pre-limiting picture, but one can think about this as a noise which comes from the branching in the system, and you see that in the coefficient in front of the noise you have both terms, so population of the let's say the mass of the population of the first type in the site K, and the second type at the same site K. So as I told you, this could be think as the limit of branching random walk with certain interaction, and just to tell you about the branching random walk without interaction. So this model is called super random walk. So you take just one type of the population instead of what was in the slide before. You have one type, branching random walks. You take order of n particles and ZD at time 0. Each particle have independent clock of branching, which rings with rate n times gamma. And when the clock rings, you have critical split or death of the particle, probability 1/2 to each event. So it's critical branching, and then you define the measure valued process, which counts number of particles in each site, divided by n, or in each set divided by n, as you wish. So it describes you the measure valued process, which as n goes to infinity converges to process y, which is called super random walk, and it's the solution to this system of SDEs. It's more or less the same as before. You just have one type, and here there's no other type present. Yeah? And the same, you run it over all sites on ZD. if you want to introduce interaction in this model, so one way to do this, you have this parameter gamma, which says you something about the rate of branching, and this parameter you may say that it depends on something. Okay, it may depend on some state of the system, and if you have two populations, the reasonable one of the reasonable models is to say that the rate of branching of particles population 1 is proportional to the number of particles in the same site from the second population, from type 2, and the other way around, which means this gamma will somehow be proportional to the number of particles of the other type. And this describes this model. We have two types. Rate of branching of any particle type K is proportional to the number of particles of the other type at same site. And again, then you have two population Y1 and Y2. This pair converges to the pair of measure value process, and this is exactly the model that Dawson-Perkins considered, where rate of branching now here is not gamma, but gamma times the mass of the other type. And this model was also constructed in the continuous, on the continuum state, where the state of particles was not ZD, it was R, and for some cases it was also constructed on R2, and there it stopped. Nobody knows up to now whether one can do it for in the continuous space in dimension 3 and higher, and even in some cases in dimension 2. So it's fascinating, since the model looks very simple, but it's not clear what to do in the continuous case, how one can make sense of this. And this was the model was constructed by Dawson-Perkins, and they also asked a number of questions about this model, mostly about the long time behavior of the model. What happens when time goes to infinity? Before I get to this, I introduce some notation. This inner product of mu and f will be just the usual definition of inner product for functions on ZD, and Zi will be always the total mass process of the type I in our setting, and Yi will always be the Dawson-Perkins catalytic process. Q will be the exit measure of Brownian motion from the upper quadrant. So it will be harmonic measure if you start at x. So distribution of the exit point of Brownian motion from the upper quadrant is given by Q. Okay, this is also notation for the whole talk. And the question they asked was about the long time behavior. Assume that the total mass in the beginning is finite, and there are two situations. OA is recurrent and irreducible, then there is a segregation of types. Just one type can survive when time goes to infinity. Okay, just one of them. And moreover, the distribution of the mass in the end is the distribution of the exit point of Brownian motion. Okay, so it will be here on the axis, and if you want to know what's the mass as time goes to infinity, the mass is one of these points, and the distribution is according to the exit measure of the Brownian motion, which is in fact very natural, since if you think about this, the total mass process for Dawson-Perkins catalytic model, then total mass is a time change of planar Brownian motion. So at the moment when it exits the upper quadrant, the evolution of the process stops, no branching anymore, and there it stays. So this is the case when A is recurrently irreducible, and in the case when A is transient, then there is a positive probability of survival of both types, which in fact means that you gain the planar Brownian motion, but the time change is not enough to bring you to the axis. It just stays somewhere here, and when time goes to infinity, and there is a possibility that one type survives. Okay. And the similar result I obtained for infinite initial conditions. When you start with infinite mass, you can also say what happens with the mass. There is also the same similar behavior, the segregation of types and coexistence of types when time goes to infinity. Now, one more thing before I start to talk about our model. The very important tool which was used in the paper is the so-called duality. It's not very natural, but what's going on in fact is that there is some function on the model which makes the model self-dual. So if I define the so-called diamond product between x and y, if I take two vectors x and y on R2 plus, I'll define x diamond y like minus sum x1 plus x2, y1 plus y2 plus I, and here differences of the coordinates where I is square root of -1. Okay, it looks unnatural, but we should live with this. This is the scalar product of x and y, where x is the function on zd, where x is the function of zd, which takes values in y, which takes values in R2 plus, and it's the same sum of diamond products. And hx1 is exponent of this scalar product. Okay, when you have this function, you may forget what is this, but such function exists, and this function does the following. If I take my process y, which is the mutually catalytic Dawson-Perkins model, take any test element y tilde in this space, then hx ty I can write as a semi-Martingale with the following decomposition. So y satisfies the Martingale problem. Okay, and on the right hand side you have very nice expression. You have h y s y tilde, and here this operator a acting on y tilde, this diamond scalar product, and h gamma y1 y2 gamma y tilde. Okay, so which means you have some Martingale problem. What is good about this Martingale problem is that it is symmetric with respect to y and y tilde. Yes, I can exchange yt and y tilde, and I get on the right hand side the same expression. This is crucial, which means that in fact this function, this y, is self-dual with respect to function h, and this means this expression, which means if I want to find the expected value of h yt y tilde, I may just calculate expected value of h y tilde t. So here I have a process y starting at y, and here I have process y tilde starting at y tilde, and this is what duality means. Okay, why it's important? For example, it immediately gives you the uniqueness of solution of the Martingale problem, which means uniqueness of the process y of Dawson-Perkins model. Since it gives you the uniqueness of one-dimensional distribution, then you can extend it to uniqueness of finite-dimensional distribution. This expression characterizes one-dimensional distributions of y in some sense. Okay? What is even another thing which we'll use and which is important, I don't necessarily need to have A to be symmetric. I can have a non-symmetric matrix, which means y tilde will be the process where the motion, this motion generator is given by A transpose and not A. This is the only difference which will be here, since I have to put A to this part. But just this remark one should keep in mind that A shouldn't be necessarily symmetric. Okay, this is the duality which we used both to show the the uniqueness, and also to analyze long time behavior of the process. Okay, now what are the questions we ask? We ask the following question: what's going on with this model? Yeah, what's going on with this model as gamma goes to infinity? So suppose now you have two populations, mutually catalytic Dawson-Perkins model, so the rate of branching of each of them proportional to the number of particles on the other side and on the same side, and whatever leads to this model. Okay? And now you say that everything goes with very high speed. Gamma goes to infinity. Okay? Is there any sense in what's going on? What will be the limit? The only thing we can say about the limit, although it also requires proof, but it looks like reasonable, that as gamma goes to infinity, then there will be only one type present at each side. Okay? This is reasonable statement and easy to conjecture that as this clock goes fast away, what happens at each side? There is very rapid critical branching on two types, type 1, type 2. Each one has critical branching very fast, which means in the end, since critical branching dies out, one of the types will die out, and the other one stops doing branching at this point. Yeah? Which means at fixed time, you definitely have just one type at each side, because they cannot be there. It's okay, even if you believe that any reasonable limit exists when gamma goes to infinity, then this product should go to 0, even if you don't think about in terms of the branching system. Yeah, if gamma goes to infinity, this product should go to 0, which means there is just one of them positive at each side. Okay, so this is more or less the picture, and but this was more or less all we could say about the limit, and we wanted to know more. Yeah, since yeah, so yeah. Okay, so this is the question we asked. These are the models for gamma goes to infinity. If model exists, we want to study long time behavior of the model, which is also a reasonable question. Whether the same type segregation coexistence dichotomy holds for this model. And the next question: what happens if there is continuous state space, which means all the random walks are now Brownian motions, and the state space is not ZZ, the state space is R. And here, just to say from the beginning, we don't know the answer. So we don't know what's going on there. It's still open, the last one. Okay, now let's turn to the first question. Yeah. The first theorem is easy to believe, again. Okay, so this is Y, which is again finite rate gamma mutually catalytic model, the first pair of equation I wrote, yeah, with finite gamma. You have on each side pair of equation which describe what happens with each type. And I define the set E, which is the set of this axis. Yeah? It's R2 plus minus whatever is inside, which means E is these two x's on the positive side. This is E. This is where where the two types take their values, or one of them is alive or another. So at each side they live on E. And then the first theorem says the following: that as gamma goes to infinity, there is a limit. There is the limit x, which takes values in this Korохod space with values in EZD, in which case I have my lattice, and for each point on the lattice, the vector takes its values on E on the axis. Yeah, since just one type is survived. Okay, this is x, which is the unique solution to this martingale problem. Okay? If you think about this martingale problem, it's the same martingale problem as here, just this term is missing. Yeah? Nothing else. But you see here the test element y tilde is in R2 plus, which means here inside the upper quadrant. Here the test element is on the axis. Okay? Which means, suppose I take here this markable problem, the test element which lives on the axis. What happens with this term? Goes to 0. Okay? Because here I have the product y tilde 1 times y tilde 2. Okay, it's a usual product. If my test elements y tilde live for each side live in E, then the product of y1, y tilde 1, y tilde 2 is 0. Okay? So this is 0 if I take these test elements. Which means this martingale problem is the same like this martingale problem. Just the set of test elements is more restrictive. Okay? This is what's going on. Then you may ask, which means, in fact, this means that y also solves this martingale problem. So I take the same martingale problem like here, and there's a set of test functions. Here I have a lot of them. Here I have restrictive set of test functions. Only test functions such that for each site in ZD, y tilde is here. Yeah? Which means I have the same martingale problem. So how can I claim uniqueness here? But since there is another process, there is a whole range of processes y for any gamma which satisfy the same martingale problem. And the trick is, the observation is, that here y lives here, inside R2. Yeah? For each side, you may have two populations, two types which are alive. Here x lives just on the axis, which means here the process is also more restrictive. It lives on smaller space. And in this smaller space, we do have uniqueness. Again, here we have y which lives, we have all the processes with values in here, since at each side two populations may be positive. Here, at each side, only one of the population is positive, which means that the process lives on a smaller set, and this in the end allows to claim uniqueness. Okay? And if you believe this, then in fact the convergence looks almost trivial, since I take this set of test functions, I get this martingale problem, and it's clear that any limit point will satisfy this martingale problem. It's also any prelimiting point satisfies this martingale problem. I just need to be sure that the limit point x is in the more restrictive space. Okay, but even if one does this martingale problem, it still doesn't answer our question, since what we really wanted to know, we wanted to know how the process behaves. And this doesn't say anything about this. Okay, it says, okay, there is a process x which solves some martingale problem. And from here, I cannot say even, maybe some people can say, but I cannot get any conclusions about whether the process is continuous or discontinuous. Okay? Yes.
Kind of a trivial question. What was known about when you have no longer lattice but just two processes? Is a known such result?
Yeah, we'll get in a second to this one. Okay. Okay. So from this martingale problem, okay, it's nice. There is a unique solution, but there is no any idea. We don't get any idea about what's the behavior of the process, how it looks like. The previous one was continuous, since it was driven by Brownian motions. This one we don't know. We would like to have some equations, since the equation gives us a sense of what's going on. And since we couldn't get any intuition about what's going on here, we decided to go to the simplest possible case. In the simplest possible case, you don't have a lattice, you just have one colony. Yeah? You have one colony, and you have two types happily living on this colony in the pre-limiting case y. Okay? take this result and, okay, no motion, nowhere to move. So which means that the limit is non-interesting. As gamma goes to infinity, again, this process is a time change of planar Brownian motion. As time goes to infinity, it will hit the axis and stays there happily forever. And you don't. This is not what you want. You want some non-trivial limit. Okay, since this will be the trivial limit which stays at one point on the axis. Okay. So what we decided to do, we decided to change a little bit this model. Still stay with one colony, but add the drift to this model. And again, if you ask whether it was known or not, we didn't find anything. So probably it was. I guess this was known. You add the drift to the system. Okay, so you take some 2 parameters theta. And wherever your point, wherever your process stays at some time, it tries to go in the direction to theta. Yeah, this is the drift. Yeah, we try to introduce drift towards theta, and just very convenient observation. You can think about this process in terms of the previous one, having 2 colonies. One colony is this one I described, and the other colony is just theta 1, theta 2, constant process. Okay, you have 2 types. The first type is theta 1, the second type is theta 2, and this I can think about this 2 colony process where the second colony is trivial, is always constant. Okay, and then I can write this equation, this c theta 1 minus y1 as again matrix A times y1t, where A is given in this form. Okay, it's not a generator, but it's still a nice metric, and can work with this metric and more or less do the same I did before. Okay, so we write this, and what we're interested in to know what's going on with this process on the first colony. And in fact, here, what we are doing, since this process is so simple, and this matrix is very simple, and we can easily construct the dual process, though I won't get into the details, but we can easily construct the dual process and analyze the one-dimensional distribution of y, and also what's going on as gamma goes to infinity. Okay? Since it's really not very difficult. And so the theorem we get, there's a theorem, yeah, but anyway. So we get that as gamma goes to infinity, this y indeed converges. But what's more, we can easily say what is the one-dimensional distribution of the limiting guy. And this is the one-dimensional distribution of the limiting guy. So which means suppose you start from x. Okay, the meaningful initial condition on the axis, since in the end the process anyway lives only on the axis. So what the process does, you start from x, then you transform the process to e minus ctx 1 minus e minus ctx 1 minus ct plus ct minus t theta. Okay, this goes to this point. And then you run the Brownian motion, since q is the exit measure of the Brownian motion. You run the Brownian motion starting from this point until the first time it hits 0. And this is your xt, the distribution of xt. This is how in distribution you build the one-dimensional distribution of the limiting process. Okay? Why this e minus ctx 1 minus e minus ct is just a solution of the deterministic equation. Yeah? Take out the noise, solve this deterministic equation, get this point, and from this point get down to the axis. This will give you xt. immediately this gives you the invariant, the limiting distribution as time goes to infinity for your process. Since you take just t equals to infinity and you see the initial condition doesn't matter, you need just to start from theta. To know what's the invariant distribution for your process, you start from theta, run the Brownian motion until the first time it hits 0, it hits the axis, and this will be the invariant distribution for the process x. Okay? So this gives you one-dimensional distribution. And one can show more. One can show the process is Markov, failure, whatever you want there. And you have one-dimensional distribution. Now the question is, you want to know what is the small time behavior, so how the process behaves on when you on the time increments. But now it's more or less technical job, since Q in fact gives you transition probabilities. So you have transition probabilities, which means if you take the derivative of transition probability, you will know the generator. If you know the generator, you know the evolution of the process. Okay, and this is what we are doing. Yeah. So we know that xt for each time behaves like this. Now calculate the generator in the usual way. You do this increment divided by epsilon. Now this, by transition probability, you apply just measure q to this function, and it goes down to take the derivative of q. Again, you take the derivative of q near the axis. Kn is the harmonic measure, and you take the derivative of q near the axis. And when you do all these calculations, and just one more remark, I didn't write the expression, but the expression for q is known. Yeah? There is explicit expression for the harmonic measure q for the Brownian motion exiting from the upper right quadrant. So I know what I should differentiate. Okay. You do all this stuff, you differentiate, and this is the equation you come from. So just for simplicity, let's take x, which is x1, 0. So suppose the process is here. You can take 0, x2, it doesn't matter, you'll get a similar expression. And okay. So we start from here. This is, let's say, xt. Here you do the increment. You want to see what's going to be next. And next, there are two possibilities. Okay, the first one is simple. The first term gives you the linear drift. There is some linear drift in the system. If this is theta, then the guy tries to move in the direction of theta in the first coordinate. Okay. The second term includes the integral with respect to some measure and something something inside. And when you see this type of integral, it immediately brings you to a conclusion that there are some jumps in the system. Yeah, since this is usually which comes out when you have jumps in the system. And this is the rate of jump. Okay? So this is the second term, which in fact one can be written as a of x2. And you divide by x1, which means the closer x1 to 0, the faster intensity of jumps. So the smaller the closer x to 0, the faster is intensity of jumps. And which means that the situation is as follows. There is some compensated jump process here, and the jump measure is nu. What is nu? In some sense, is derivative of q. You take this harmonic measure q, which brings Brownian motion to the axis, and take the derivative of this harmonic measure near the axis, and after rescaling you you'll get measure nu. Okay, and this measure nu clearly also gives its masses to the axis. You see, OV is 0, which is the second coordinate, OU is 0, which is the first coordinate. This measure nu also always brings you to the axis. No matter where you are, you'll get back to the axis. Which means what's going on? X1, there is some kind of continuous path here in this motion, and when there is a jump, there is measure nu, which brings you or to this axis. This is the first part, and you see that this measure is infinite, so you have infinite number of jumps on any compact. So it's one can think about this nu in some sense as a Levy measure. It's a kind of Levy measure. The process is not with independent integrals, but this is the measure of jump, which is very similar to Levy measure, and you see that this measure is infinite near 1. So it's you have infinite number of jumps. So, and the measure brings you or to this axis, or occasionally it brings you here. Yeah? So which means that you may have two possibilities. You move here, or you jump here and there, or sometimes you jump to this axis, which means that type changed. There was type 1 in this colony, and from now on there will be type 2 in this colony. And if you take about the pre-limiting picture, or somehow what's going on, the type tries, so your equation tries to get out of the axis. When it tries to get out, the Q measure immediately tries to bring it in. Where it tries to bring it in, usually it brings you in here. But occasionally it may bring you here. And this is what's going on with the process. It tries to get out of the axis, it jumps around its position, and sometimes it goes here. Okay? This is since it somehow changes its position by measure Q. It tries to get out, it comes here, and then it goes back. So which means that in the end, this is you'll get the equation. You get this stuff which comes out from the motion of the mass, and these martingales which in fact the pure jump martingales. So I described here just the jump structure, but there's also a compensator which brings everything to be a martingale. So in the end, you have this type which comes from the preliminary equation, and these martingales which before were martingales driven by Brownian motion, and now the martingales which are driven by some jump process. Okay, and I'll describe just in the next slide. I'll describe more about say more about the jumps. So maybe I'll skip this step. Okay, let's do it this way. So, which means if we are here, then there is a jump, and the jump are with this intensity. Okay, you have AX2 1 over X1. Okay, this comes from this term, and the jump itself, it's all this or this. Okay, since or y1 is 0 or y2 is 0. Okay. Suppose y1 is y1. Suppose y2 is 0. y2 is 0. What does it mean? y2 is 0, which means that the second population doesn't jump. It wasn't 0. It stays in 0. This means that y2 is 0, and the jump of the second population is 0. If y2 is 0, then the first population, the mass of the first population changes. How it changes? You take the previous one, multiply by this, and minus 1, you get this is the jump. If this is the jump, in other words, it means that x1 jumps to y1 x1. Yeah? You take the previous position plus the jump, it gives you this. Which means you take your previous position x1, x1t, and the jump will move it to y1 x1t. Okay, where y1 is given by the measure nu. Okay, and x2 goes to 0. It was 0, it stays 0. Okay, another possibility is that y1 is 0. If y1 is 0, then the jump is minus x1t minus, which means x1 jumps to 0. So the first type dies out immediately, but you recover the second type, which jumps to y2 x1 t minus. Okay? Where y2 is again distributed to the second component of the measure nu. So altogether, if you started here, you jump to y1, y2, x1t, where again, only one of them is non-zero, which means you jump out of the first component, or the first component changes, and the second stays 0, or the first component goes to 0, and the second gets to be non-zero. So you put all this together, you get that this is the expression for your jump, and you write the SD, the system of the SD for the first colony. Okay, all this was to get the intuition how the limiting process, to get the idea how the limiting process looks like. So we get the limiting process for one colony model. But it's clear that in multi-colony model, infinite colony model, the situation will be exactly the same. Just here you have one colony. There you have a lot of colonies. But at each colony, the same thing will happen. We'll get exactly the idea what's going on each colony of infinite colony processes. It will move with, there will some kind of deterministic equation which is given by A, and the jump process which governs the jumps at each side of ZD, which means, again, what's going on, you always have only one time present, and the position of the type may change continuously a little bit, and but more dramatically, the noise time is on the noise part is on the jump of the process. So that's what I want to say. For infinite colony process, you take this is pre-limiting Dawson-Perkins process. Then you define the rate of jumps. Okay, this is the rate. Again, the rate is A of x over x1, depending on the type. And you write the theorem, which says that as gamma goes to infinity, y converges to x. Sorry, it shouldn't be A here. It's Mélegène topology, where x is the unique weak solution to the following system of SPDEs, where again I stress this out that this is the same system of SPDEs that we had for one colony. We just put it for many colonies and say that all this makes sense. So this is a lot of work to show that this is exactly what happens, to show that the limit here. And again, this the martingale measures with this intensity. So this is the intensity of jumps. This is where the jump goes. And this is ds. Okay, you have intensity of jump, this kind of analog of Levy measure, and which brings you to know to which point the process jumps. And just a few words about, okay, just one word. So this is Mélegène topology, which means you don't converge in Skorokhov topology. Why? Since the pre-limiting process is continuous and this process is discontinuous. Continuous processes don't converge to discontinuous Skorokhov topology, so there is topology weaker than that one, which allows you to make these things work, but it's not the most interesting part. So how the proof goes. Okay. First one shows that, remember there was a martingale problem which didn't say anything about the behavior of the process. Okay, you show, okay, that the y converges to x, which is solution to this martingale problem. Okay, this is the first part. Then you show that there is unique solution to this martingale problem. This is duality, as I said, explained before. So you have some duality relationship. It's not trivial, but one can show this. Okay. Now, it's not easy to show that directly that y converges to x, which is solution to the system of SDEs. Yeah, it's not easy, since you have all these equations which are driven by Brownian motion, and then you want to get something driven by jump process. But what you are doing, you construct this system of SDEs. Okay, there are a system of SDEs driven by jump process. You have a lot of small jumps. You subtract small jumps. You define approximating sequence of processes without small jumps. It converges here. The only thing you want to show that this process is the same as this one. But this is just a formula. You take this process, apply this function, and say that it solves this martingale problem. You have some SDs, so formally you can use either formula. Use either formula, apply it there, and so okay, the process which does this, in fact, solves this. But there is a unique solution to this one, which means there is also a unique solution to the system of SDs. Okay. This is more or less the strategy of the proof. Now, the last thing is the long-time behavior. I remind you, if you forgot, that for the pre-limiting proof for Dawson-Perkin process, there was dichotomy. Whenever the process was A was recurrent and irreducible, the types couldn't survive together. One of them survived. And when A was transient, then there was positive probability for survival of both. Here we have a bit more delicate situation. This should be the x. Sorry, this is the limiting process. This is supposed to be x. So again, assume that the total mass is finite. And again, when A is recurrent, the situation is the same. They cannot survive. But the transient case is a bit more different. We cannot show, what does mean transient? Transient means that green function is finite. Okay? And we couldn't show that whenever the green function is finite, then there is a positive probability of survival. We could show something less. We had some function which is similar to this one. It's a bit more difficult, but morally it's this one. You have a green function. It would be a green function, but you have here log. Okay, so you have log correction to your green function, and this one not only you assume that it should be finite, which is already more the stronger condition than transients, but you also assume that it should be sufficiently small. Sufficiently small you describe in the proof. But if this is sufficiently small, then you can show that there is a positive probability of both types survival. And this leads to an open question whether it's possible to have, when A is transient, that they die together. We don't know the answer. And we still don't know the answer, but just a bit insight why this may be plausible situation. The situation is as follows. In the Dawson-Perkins model, we have finite variance. We have 2 moments, 3 moments, 4 moments, whatever number of 2 moments for sure you have. Yeah? And here, in this model, there is no second moment. So the second moment diverges. So if I take the expected value of z squared, everything blows up. So up to 2 moments we have, but only up to 2. For 2 it diverges. And this and it's known that whenever you have less moments, then you have some of this threshold is moving from the transient case. It's known for the populations with heavy tails distribution. And it might be that this is the reason. If we don't have the second moment, that indeed we need to require more than transients to get the possibility of survival. But here we don't know what exactly. We don't know exactly the answer. This is the best way we know up to date. Okay, so I guess I would like to stop here. Thanks a lot for your attention.
Questions, comments?
You have, I'm still trying to capture intuitively how, the one can take over from the other one. If the one type is established in the site, and it simply kills off everything immediately. Rather curious.
Yes, very curious. We're fascinated. But it somehow moves there, and then what's going on? You have the mass which tries to come from the other sides. Yeah, this is what A means. In fact, that's the drift. The mass tries to come, and at certain point it wins. At certain point it means, but it means in a jump type. So it means such that it kills immediately the first type, and the second type established from nowhere.
Is there?
It's not continuous type.
Is there some kind of large deviation hidden in here that somehow the migration is somehow exceptionally big at some point, that it's enough to take it over?
No, I guess it's kind of it should be the lack of moments of for the exit point of the Brownian motion. You have the Brownian motion doesn't have moments, so which means the exit point, which means the CLT doesn't work here, which means whatever you try to do, in the end you will get jump process. This is my understanding why you get the jump in the end. Yeah, since you try to add up this, you try to add up these small increments which come from the harmonic measure of Brownian motion. You try to add them up, but in the end you get only jumps. When you are trying to exit, and this which brings this to the jump process.
Awesome. All questions? If not, let us think again.